This video is on states of matter. So, in our world, we have three basic states of matter. We have solid, gas, and liquid. Right? These are the three basic states of matter. And now we're going to look at the processes between that convert between states of matter. Right? Now, if you consider a substance X, at its coldest temperature, it's going to be solid, and then it's going to progress to liquid, right? And then it's going to become a gas. However, sometimes some substances skip the liquid step, right? They go from solid directly to gas, right? And as a substance cools, it, it can go from gas to liquid and liquid to solid, or gas to solid directly, right? So let's look at the conversions between three states of matter. So we're going to put processes that require heating in red and processes that require cooling in purple or blue. So as a substance, let's go in linear order from solid to liquid, right? As a substance heats from a solid to liquid, it's called melting. Okay, right? And as a substance heats from a liquid and becomes a gas, it's called boiling. Okay, and a solid directly becoming a gas is called sublimation. Sublimation. Right? These are the three heating processes. Now let's look at the cooling processes. They're going to be in dark purple. Right? So as a substance cools from a liquid to become a solid, it's freezing. It freezes. And as a substance cools from a gas to a liquid, right? This is condensation. Condensation. Now, as a substance cools from a gas and directly becomes a solid, there are two names to this. In IGCC, we prefer deposition, right? But you can also sometimes hear desublimation, right? You can either remember it as sublimation and the opposite as desublimation, or you can think of it this way. As a gas cools, right? Cools, this is a gas, imagine. It's going to form deposits of the substance in the solid form, right? It's going to form deposits. So as it cools, when a gas directly becomes a solid, it forms deposits, right? So it's called deposition or deposition, right? These are the three cooling processes. Now be very, very careful to not get confused between boiling and evaporation. They may look similar, or they have similar ideas, or they may look similar in reality, but the processes or the methods by which they change state is very, very different. In boiling, the substances form bubbles underneath the water because the substance turns to gas. I mean, underneath the surface of the liquid, right? Substance turns to gas throughout the liquid. It can happen on the surface, it can happen under the surface. In evaporation, what happens is if you have a tray of a liquid, a fewer higher speed molecules, okay, relatively higher speed molecules escape and then form part of the air, right? Now, because they escape, this causes cooling. Because if you think about it this way, right, you have uh, two, 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 and then you have three, right? The average is not going to be, uh, it's not going to be two. It's going to be 2 point something, right? Now, if the three escapes, right, you're going to have 2, 2, 2, 2. So the average is 2. So the temperature dropped, right? That's why a higher speed molecules, that means they're at a higher temperature. Because temperature is the measure of the average kinetic energy, right? This is what temperature is. So that means the total kinetic energy drops. So average drops. This is what happens in evaporation. In boiling, this substance itself, they don't gain kinetic energy. They don't gain kinetic energy. This is not what they gain. They gain potential energy, right? We'll come to this later when we discuss heating and cooling curves, but you need to know that boiling is due to the gain of energy and not due to, and causing, it results in heating, not in cooling, right? Now let's look at the different properties. So we have a solid, a liquid, and a gas, right? Now let's look at three flow. The properties can very easily be linked. So you have volume, shape, right? Compressibility, the result of a change in temperature, okay? The density, the speed of the molecules, the force of attraction between the molecules, or whatever particles, can be atoms as well, right? The structure, the collisions or frequency of collisions, and you have then motion, right? You have then motion. We'll look at these later, but let's look at these two first, right? It's fixed in solids and liquids, but in gases it's variable. And in solids, the shape is fixed, but in liquids and gases, they're variable. Now, this is because the force of attraction in solid are the highest, right? And then it's pretty high in liquids, and it's almost negligible, okay? In gases, almost negligible. What this means is that as there are two particles in a solid, right, then the force of attraction hold them and bind them together really tightly. Think of it as a very strong rubber band around two fingers, right? You're not going to be able to stretch that rubber band because it's really, really strong and it's really thick, right? But then a very, very thin rubber band, you'd be easily be able to stretch it and you'd be able to even maybe break the rubber band, right? Just with those two fingers. That's because it's much weaker. So in a gas, it's a very thin rubber band, but in a solid, it's a very, very thick rubber band, right? So that's what's going to cause it to have a fixed volume and a fixed shape. It has a fixed volume because it can't expand as a solid because of the thick rubber band, right? You can only expand it so much. But in a gas, they can break free and they can move wherever they want. So the volume can vary. Likewise, well, with liquids, molecules they slide over one another. But they're not fixed in position. They slide over one another, but they can't escape. They're gonna, they still have, they're still very tightly packed. And now in solids, the structure of the atoms, they're very tightly packed, and they're in a very regular structure, right? They have a very regular structure. It's grid-like. In liquids, their structure is closely packed, and here they're free to move. Right? And gases. So this is uh, what causes the shape to change. Now, because these force of attraction are so strong in the solid, they have a fixed shape. They can't move over one another. But if when we look at the motion of liquids, right, in solids it's just a vibration in place. In liquids, they slide over one another. That means they can move around each other, right? So if they're moving around each other, that means they can change shape, right? So if you have, let's say, two finger, you keep all your fingers in like really tightly packed. You can't move them around, right? But if you make them a slightly looser, they're still close together, but you can move them about one another, right? So the shape changes, but it does not expand. That's why it has a fixed volume but variable shape. In a gas, imagine you take your two hands, right? You keep two thumbs. You can keep them close together, but you can also keep them really far apart. Simply because they're not really linked, right? So that's why in gases the have variable shape and variable volume, and the motion in gases is random. We look at that later. Now, knowing all of this, obviously the compressibility of solids is going to be none. They're not going to be compressible. Liquids will be, because they have slightly more room, right? They can wiggle around and move around each other. They have slightly more room, so they can be compressed, but not as much as gases. If you take your entire room, right, all the air in your room can be compressed into a very tiny space, because that's how um, rare it is. So let's look at the density, right? In solids, they're extremely dense, right? In liquids, they are dense, but not as dense as solids. And in gases, they are rare. It's, uh, it's almost like a couple. If you take a paintbrush and you spray a couple of spray some paint, just flick a brush on top of some paper, there'll be a couple of specks, and they're going to be spread out. They're not going to be very close together, right? That's how gases look. Now, this is called temperature, right? This symbol here, theta. Theta represents temperature. This is in degrees Celsius, right? And delta, this represents change. And these are two very important symbols to know in physics and chemistry. Okay, very important. So, looking at the result of a change in temperature, in solids, there's a very slight change in size, very slight change, as in a slight increase, or when the temperature increases, or a slight decrease when the temperature decreases. But it's very slight, right? You needed thousands of degrees of change or hundreds of degrees of change to actually be noticeable to naked eye. In liquids, they also have a very slight change in size. But gases, because of the very low, almost negligible force of attraction, they are very greatly affected by a change in temperature. Okay, so that's a very great change. Now, please remember While the force of attraction are negligible, almost negligible, they are still significant. You cannot write that they do not. They are significant. They are present. It's just that they're not very, very, uh, they don't really work as much as solids and liquids. Now that we've looked at the change in size due to the change in temperature, let's look at the speed. Right? Now, the speed in the solids, or the speed of the particles in the solids, are the least, and they're the highest in the gas. And in liquids, they are more than solids, but in gases, they are the most. Right? They're very high in gases. And with speed, okay, now these particles are traveling at high speed, right? Eventually, they're going to collide. This is what causes the random motion, right? We said random motion, we'll talk about that later. The random motion in gases is caused because these particles are traveling at such high speeds. See, in solids, they're moving about the same place. They're very, very slow motion, right? And they're just vibrating. So there's no collision per se. In liquids, they're moving around one another. They're moving like this, right? They're not moving at a very high speed. So they don't really, when they collide, it doesn't cause that much of a change in motion because they're touching, but they're very close, but they're not touching. Right? They're very close in liquids. So that's why the speed in liquids is not that high. In gases, there's a lot of space so they can move around. And then when they collide, it causes random motion. So collisions in gases are, however, collisions in gases are the least often relatively. Okay. In liquids, they are the most often. Okay. I mean, there are two arguments to this. In solids, we say that there are no collisions happening because they're constantly touching, right? But you could argue that there is a constant collision that's happening. But in IGCSE, we say that there is no collision that happens in solids. They only happen in liquids, and liquids they are the most often. In gases, they happen very infrequently in relation to the frequency of liquids because of the density of the particles in a liquid as compared to a gas. Right. So now we've looked at the properties of solids, liquids, and gases. Next thing on our agenda is the kinetic particle theory. Now, there are four key things in the kinetic particle theory. First, all matter is made of tiny particles, right? And these particles are moving. Second thing is particles are constantly moving, right? These are very easy to remember. You can remember them very, very easily. These are not too uh, hard to remember. The next two are slightly more difficult, especially if you're not used to the idea of the kinetic particle theory. The next thing that it says is the higher the temperature, the faster the motion of the particles. And this is because we said temperature is a measure of average kinetic energy, right? Kinetic energy is the energy of motion. So usually when something has more energy or when they have more energy, you would think that they're moving further. Okay. But think of it this way. If they're running a race, they have a set distance, right? In a race, the idea is to be the fastest. Right? So they can run. They have, if let's say there is A has to run this and B also has to run the same distance. Now A has more energy than B. Now A will obviously run faster because it has more energy to run faster, since the total distance is the same, right? So that's why higher temperature, means that there's a higher average energy, is to faster motion and not a longer motion or more distance. This is why it is not more distance. Now, fourth thing that we're going to look at is heavier the particle, the slower the motion. Now, you can think of it this way, right? Let's say we have a person A. Okay, you have a person A, and then you have a person B. The only difference between these two is that person A weighs 50 kilos and person B weighs 100 kilos. The rest, their height, everything else is the same. The amount of energy they have is the same. Okay. Um, this is not intended to fat shame anybody, but this is just for ease of explanation, right? Now, if they both have the same amount of energy and they both have to run a race, we said that they would move faster, right? Now, the reason person A moves faster than person B is because person A requires less energy to move to move his body, because there's less mass. Okay, he has less mass than B, right? B has more mass. So that means that he requires less energy to move his legs. B requires more energy. You can think of it this way, okay? For your car enthusiasts, if you have a massive truck, okay, you have a massive truck like this, and then you have a tiny hatchback. Okay, now the hatchback is much smaller and weighs, this is maybe 1 ton. This is 50 tons. Now, obviously, the hatchback can move faster, right? It can choose to move slower, but let's say they both were traveling at their highest speed. The hatchback will be faster, right? Simply because it requires less energy to move the same distance, because there's less mass to be moved. Since there's less mass to be moved, the total amount of energy utilizes less. So the thing that is heavier, that means it has more mass, that that substance will move slower than something with less mass or something that is lighter. Right? Now, obviously, if, um, talked about set distance, but in particles they don't have a set distance. So as they move faster, if there were two cars that were traveling, one was traveling at 60 kilometers per hour, and the other one's traveling at 80 kilometers per hour, and they were at this, and they let go of the accelerator and the brake at the same time. They both are on the same road, same thing. Obviously, the one traveling at 80 kilometers per hour will go further, right? Simply because it has more momentum. So it may be the case that the one with more energy can uh, move further, right? The one with more energy can move further, but that is because of the momentum. but it's very unlikely, simply because it's very unlikely that they're going to have an empty road where no cars are going to come in between, right? There are going to be cars that come in unless the cars move away, but particles are not going to move away for another particle. They're going to collide, right? So that's why this is a very important kinetic particle theory. The last thing we're going to look at for today are heating and cooling curves. So imagine we have a graph, right? Uh, a heating cooling curve is going to be a temperature time graph. Temperature, this is theta. Temperature is going to be on your y-axis, and time, it can be in minutes, seconds, hours, whatever. Doesn't really matter. I'm going to use seconds because that's the SI unit. Right? Time is going to be on the x-axis. Now, forgive me if my line, because my lines are not really very straight, but it's just a rough drawing. Right? So let's look at the graph. It's gonna look something more like this. Let me use a different color so it's very easy to see. Gonna look something like this. Obviously, these are going to be straight lines, and it's going to continue. So there are three sections, I'd say. No, five sections actually. So you have this section here, this one here. You have this section, this one here. You have this section, this one here, and you have this section here, and then you have this last section here. Right? So we're going to write the states of matter. I'm going to write the states of matter, and then I'm going to explain why it is so. Right? These are the states of matter. So at this point, okay, imagine this is the starting point. So the substance is being heated. Now, at this point, this is going to be the melting point. Okay. Now, the reason this is a flat line is when a substance reaches, the reason we have a set melting point and it's not a range of temperature is because once the melting point, or a boiling point as well, once this is achieved, right, they are not achieved, they are not going to increase the temperature. The temperature will remain the same until the change of state occurs. Until the change of state. So at the melting point, it's going to be solid, and then some of it is going to turn into liquid, and then some more will turn into liquid until everything is liquid. The moment everything is liquid, the temperatures start rising. Right? So that's why we say this is solid and liquid. Likewise, once it hits the boiling point, there's some of it is going to turn into gas, some more is going to turn into gas, until everything is going to turn to gas, and then it will keep rising. The temperature will keep rising, and now there's not going to be any more points, because once it's a gas, it will keep increasing continuously, right? So this flat line, the first flat line, if it is between solid and liquid, it is the melting point. And this is for a heating curve. Okay, we are considering a heating curve here. This is a melting point. It's between liquid and gas. This is the boiling point. Now, how do you know if it's a heating curve or a cooling curve? Heating curve, temperature will rise. So gradient will be positive. Positive gradient means it's moving to the right, like this. Okay, this is a positive gradient. So we said temperature is a measure of the average kinetic energy. Now when you boil water, you have a pot of water, right? You have a pot of water, and you're going to have some flame. Okay, you're going to have some flame that's providing heat. Right? It's providing heat, and that heat is still being supplied when the water is boiling. Even as the water boils, right? It's still the heat still supplied. So if the temperature doesn't rise, what's happening to that energy, right? The heat energy that's being supplied, what's happening? So as the temperature rises, it's the particles absorb it as kinetic energy. But once the the melting or boiling point has been reached, right? The energy is absorbed as potential energy. This is for breaking the physical bond. Okay, breaking the physical bond. This is how. Uh, this is why energy is still being consumed, but there's no rise in temperature. Now, the same thing will apply for a cooling curve. Now, please be very careful when you write your answers for a cooling curve. In a cooling curve, the uh, temperature is decreasing, right? So that means energy is being given out. It's not being taken in. If energy is being given out, right? How do you know if it's kinetic or potential energy? The same logic applies. When it's a flat line, it is potential energy. When there is a gradient, it is kinetic energy, right? Here, let's label it here. This is going to be kinetic energy. This is going to be potential energy, kinetic energy, potential energy. This is going to be kinetic energy. Okay. So a cooling curve is going to look something like this. Oh, oops. Okay. It's not going to look like this. So yeah, cooling curve is going to look like this. Right, something like this, and then it'll continue below. So here, now you need to make sure that you know the segments properly. Here it's going to be a gas usually. It can be liquid also. Even for heating curve, it can start as a liquid. You need to see how many points are there, how many melting and boiling points are there. That will tell you what state. Or usually they will label it as well. Here it will be liquid. Here it is solid. Right? And here it is going to be gas and liquid. Here it's going to be liquid and solid. This is the when it turns from gas to liquid, it's called the condensation point. Okay, this is the condensation point, and this is the freezing point. You cannot write boiling or melting. It is freezing and condensation point in a cooling curve. Right? Here potential energy is being gained. Here potential energy is being gained. Here kinetic energy is sorry, it's not being gained, it's being lost. Potential energy is lost. Kinetic energy is lost. Okay, I'm very sorry. So energy is being given out to the surroundings. So because as the physical bonds are forming, they're not breaking. As they're forming, they are giving out the energy.